Hey everybody, and welcome back to Linear Algebra Online. So today is a really important video because we're going to talk about arguably one of the most useful, most powerful tools from linear algebra, and that's something called an isomorphism. So the definition just basically says an isomorphism is a type of linear transformation that sends v to w here. And it's just one that is one-to-one and onto. And if V and W are two vector spaces where there is an isomorphism between them, then we say that they are isomorphic to each other. So isomorphism is the map, isomorphic are like when you're talking about vector spaces. One thing I don't think the book does too well is explain what this means. What this basically gives us is that if two spaces are isomorphic, then they are structurally the same thing, and all the math that you kind of do with one vector space can basically be done similarly with another one. So there's a lot of things in math where it's really hard to work in one space, but we maybe make this special kind of one-to-one and onto map to like another space where it's easier to do some sort of math. And then we should have a way to go back because it's one-to-one and onto. We're not going to lose any info when we switch between them. And so basically it's just a linear bijection between two vector spaces. And when you can build that, then you have the power to know that those two spaces are basically the same thing. It's, just sort of been like at the core of stuff like what we've been doing with like polynomial spaces and like Rn. So, we're used to these kind of things where we've seen problems where it's like if you have like P2, we think of so here, I'll just write it this way. So in P2, we think of maybe, the quadratic 1 plus x plus 3x squared. And we've been sort of talking about it as like the vector 1, 1, 3, right? An isomorphism between polynomial space and P2 in this case and R3 is what really gives us the power to do these kind of things. And, this is a good example of where it's easier to work in this space than this space, because here in like R3, you can like utilize, this column vector and do like matrix operations on it. You can plug it into a computer and do like RREF and the simplified thing. But like if we were doing that with a quadratic, it's kind of confusing, right? It's like, it seems odd to think about how we could like use a matrix to work with a quadratic. That's like a weird sentence, right? So what we do is we interpret this vector as 1, 1, 3, kind of the vector that you're used to thinking of. And then we do math over in this space, and we get a result, but then we interpret it as a polynomial in the end. So that's something that I don't think the book does a great job explaining, like why we're even building these maps between spaces, but that is why. Basically, we want to, in a sense, cheat something and work in an easier space like Rn, do a bunch of math, and then switch back and interpret our result in the original like polynomial space or whatever the thing is, okay? And so I want to like show today just kind of how we go about like literally proving that two spaces are isomorphic. It basically is it takes two steps, really, is how it works. You really need to show, it's technically three things, but I'm going to give you a theorem here in a second that we can use, and I'm not going to prove it in this video because it just takes too long. But if you have this one theorem, basically all you're going to need is really two things. But technically, to show an isomorphism, you need to show that the transformation you're building is linear, okay, which, that really has two parts to it also. But then you also need to show your transformation is one-to-one and onto. So the reason we can do this a little quicker, though, is there's a theorem in the book. I think it's on page 490, if you want to look. And it basically says let the dimension of V equal the dimension of W, and just like say the N, okay? Then a linear transformation T from V to W is 1-to-1 if and only if it is onto. All right, so if you think about this, basically what we're getting here is if two spaces have the same dimension, which is easy to see, okay, then you can just literally count the basis vectors for each one. If you show that it's linear transformation, so you will have to show that part for sure. And if you show that it's 1-to-1 or onto, you get the other one for free. So that's kind of the power of this stuff. So what we're going to do is we're going to show our transformation that I'm going to propose here in a second is linear, and then I'm going to show that it's basically 1-to-1, and then I'll get onto for free. And so then I have all three parts of this definition satisfied, so the two spaces are isomorphic. Okay, and I'll talk about this funny thing in a second. To do this, I'm going to start off with the linear part. So I'm going to need some polynomials. So I'm going to let P of X equal that. So just like, standard, we're in n-1 polynomial world. So just add up a bunch of these are constants, right? And then I'm going to actually need another one too. I'm going to let Q of X equal that. And what I'm basically going to do is I'm going to propose a map here in a second. I'm just going to show that it is linear. Right? And so the kind of obvious choice is I'm going to prove here that T of P of X, I'm just going to be lazy and write P of X. So that whole big, n-1 order polynomial. I just want to send it to the vector a0, a n-1. So this is just how we've been basically, going back and forth. And now I'm going to formally show that this kind of map is actually an isomorphism. And so really these two things are the same thing is the idea. So, so to prove this, you got to do two things, both the show that scalars can kind of be pulled out, and then you got to show that the transformation on a sum is the same thing as the sum of the transformations, right? So let's just do the scalar first, okay? So T of C times a polynomial in there. Did I have too many parentheses? Nope. Is just going to equal, based on this map, C A0, C A n-1. But of course, that means you can pull a C out, and then you get A0, A n-1. And that is, of course, C times T of P of X, right? And so that is proving the first part, right? That of linear. So we can pull a scalar out, right? And that's nice. To show that the second part of linear, I think I'm going to have to erase this top part, so I'm going to do that. So now I want to just show that T of P of X plus Q of X equals the sum of the transformation on each of those, right? And so just based on this map I've defined, this would be equivalent to A naught plus B naught, and then A n-1 plus B n-1, which is, of course, because how column vectors work, you can split that, and then add to that B naught dot B n-1. And that is, of course, T of P of X plus t of q of x. And so that's the other part of linear. So I now have that, this transformation right here, this thing is actually linear. These problems take a little bit of writing, so I'm sorry it's taking up a lot of the page. But so that is one of the two things that I really got to spend some time showing. The other part I got to show is either one-to-one or onto. It really doesn't matter. I think I'm going to erase now the constant part at the bottom and show the one-to-one part down there. All right, so I'm just going to start off. I'm going to let p of x basically just be sent to the kernel, okay? Like go to 0, and I'm just going to show actually that the only thing that will work here is actually the kernel is going to be the trivial 0 vector. And so that would imply one-to-one, right, based on a theorem we saw in the last video. So, based on this map, this is going to say that, like, a naught, a n minus 1 equals, 0 vector, which here is just, zeros all the way down. And if you think about what that means, then a naught has to equal a1, which has to equal blah, blah, blah. N minus 1, all of those have to equal 0. So the kernel of this map is actually just the trivial, 0 vector. And so we have this theorem that says if your map is a linear transformation, the kernel is the 0 vector, then that is equivalent to being one-to-one. So T is one-to-one. Thus, by that theorem I wrote before, I'll say it like this. So thus, since dimension of V, I'll just use what they really are. Dimension of p n minus 1 equals dimension of r n, both equal m. T is also onto, so T is an isomorphism. And so that's basically the feel of these problems. It's like you technically have to show 3 things, but you get one for free based on a theorem that I didn't prove to you, but there is a proof in the book. It's pretty quick. It really just uses like the rank theorem. It's not too bad. But so you want to show that it's linear, you got to do that, and then I usually do this trick to show it's one-to-one, and then you get onto for free because it's a linear map. And that's really nice because now these two spaces are structurally the same, which lets me work, with an easier space, Rn, rather than working with Pn minus 1. So there's a bunch of other terms here that are not in the book, but I kind of wanted you to see them because they're actually all very related here. So this is getting into a huge area of math. I mean, this is really the start of a lot of pure math, and it's honestly what mathematicians basically spend their time doing. We basically really try to build maps between spaces, like on the most simple level. I have a joke that you can basically get a PhD in math if you, if you take 2 structures, and you can basically get a PhD in math sometimes if you just can show this arrow. It's kind of like the PhD arrow. And that can be really, really hard to show that a special kind of map happens between 2 spaces. Is sometimes enough to get you a PhD, literally. You can just write a paper about that, and that's good enough and give you a PhD. These arrows can be all sorts of different things. You can read about these online. I'm never going to test you on all these things. So this joke is something that I have vivid memories of, because I would make some sort of map. So a homomorphism is a structure-preserving map between two algebraic structures. But sometimes that thing is not an isomorphism. And isomorphisms are, the ones that we just talked about, where they are one-to-one and onto between these vector spaces. That's kind of the best case for vector spaces. But sometimes you get other things, like an automorphism is, that's not the one. I mean, a monomorphism is an injective homomorphism, but it might not be surjective, and so it might not be an isomorphism, all right? The automorphism actually is an isomorphism, because this is one that you could always do the identity map between, these are between, a space V and itself. So if you just identify everything here with the same element over here, it kind of trivially is a isomorphism. But there's these two at the bottom are the two that I kind of wanted you to just see. So if any of you go into kind of the more applied sides of math, you will be building diffeomorphisms. So they're just isomorphisms between smooth manifolds. Basically, think spaces where you can do derivatives, honestly. That's kind of how you want to think about it. Then there's homeomorphisms, which are the ones that are kind of closest to my wheelhouse. These are isomorphisms between topological spaces. So this was what I spent so much of my 20s basically spending time doing. And I do have a paper where I basically built a map between two topological spaces, very complicated ones, and that honestly can be a really hard problem. So there's all sorts of these out there. You can read the Wikipedia pages on them and stuff, but there's a lot to say. I just wanted you to see some of these other definitions. All right. So another theorem that I think you should read the proof of, that I'm not going to get into in this video, is how we can just know whether or not two spaces are isomorphic. So it turns out if you have V and W are two finite dimensional vector spaces, really over the same field of scalars too, that's important. Then V is isomorphic to W if and only if the dimensions of them align. So this is honestly a lot of times pretty easy to figure out. But if you can determine that two spaces have the same dimension, then you're going to get isomorphic for free, okay? But this does not say anything about what the isomorphism is. So this just means we know we can find one, but that PhD arrow thing I was saying, we actually have open problems in math right now that we know two spaces are isomorphic, or diffeomorphic or things like that, but we can't actually get the map yet, and until we get the map, we wouldn't be able to transfer between spaces nicely. So so this arrow part that I was talking about is key to a lot of higher level math right now. So just to kind of show you what I mean by this, so if you have W be the vector space of symmetric 2x2 matrices, and we have R3, then those two spaces, right, are they're going to be isomorphic, because if I take a basis for W to just be the set of matrices 1, 0, 0, 0, 0, 1, 1, 0, because it's symmetric, right? And then 0, 0, 0, 1. Those things, there are, 3 vectors there. And then for R3, of course, we would just take I hat, J hat, K hat, right? So they both have 3 basis vectors, so their dimension is 3. So they are isomorphic. But sometimes it is hard to think about how we would, send the two spaces back and forth to each other. Here, the way that we would do it is actually not so bad. This is a nice, easier example. but they can get really, really complicated. Here, basically, if I was proposing an isomorphism between the spaces, I would say just let T of any random 2 by 2 A, B, C, D. Sorry, I don't want, there's from metric, sorry. We want a BB, C, right? So the way to just do this is just take any random symmetric matrix and just send it to A, B, C, right? If you go through and like show this map is linear and then show like the kernel is trivial, you'll get 1 to 1, and then from that fact that it's linear and the kernel is trivial, you'll get onto. So that would kind of be the next steps. I'm not going to go through it all here, but the next steps would be to prove T is linear, and then that the kernel of T is the 0 vector, so T is 1 to 1 and onto. That's kind of the plan for all these problems. And honestly, that's the plan for if you go on to math professionally, become a mathematician. This is so much of what mathematicians really do. It's pretty cool that I can finally show you what a lot of us spend our time doing, basically. So this is sort of like how a lot of these problems feel with these isomorphism problems. You literally have choice on this. You propose these maps, and then you just go through all that stuff. And this is an important like precursor step, just so we know that the spaces have the same dimension, and then we can get into all this. All right, so I did want to go through just one more like example in full detail here. So we're going to say D sub 3 is the vector space of 3 by 3 diagonal matrices, and then we got R3 over here, and the dimension of D3, you would just need 1 for every diagonal, so you need 3 basis vectors for a 3 by 3. So that should be isomorphic to R3. So that we know that, so you could argue it that way. So the dimension of D3 equals the dimension of R3, which equals 3. So yes, isomorphic. And I'm going to propose a map, and then I'm going to go through the full like proof on this one of showing the two of them really are iso. That is actually a term we sometimes use to sound cooler too. We say, yeah, these two things are iso. But anyways, so the map I would propose, I'm going to let T take ABC down the diagonal, and then just zeros elsewhere to A, B, C, right? It's probably the obvious choice. And so I want to go through, the full proof here and show that you've got a linear map and that its kernel is trivial. So we go 1 to 1, and then we'll get on to out of that for free. So, all right. So this is kind of the plan of attack. I'm going to let A be this diagonal matrix, just like A11, A22, A33, just down the diagonal. B, B11, B22, B33, just like a different diagonal matrix. And I'm going to show the linear part just all in one step. So I'm going to show that this will basically simplify to C1 T of A plus C2 T of B. That's the plan, okay? Because then I show all in one step that scalars can be pulled out, and the sum of two vectors, the transformation of the sum of two vectors is the transformation on the sum, okay? So that's going to be what I want to get to at the end, so I'm not going to write it there. If I just go and put all this stuff kind of in, right, you're going to do like C1 times all this, C2 times this, and then you're going to add them, right? So you'll get this, right? So that's just adding these two things together. You just got zeros elsewhere there in the corners. Then the transformation, based on this map up here, says that we're going to go to the column vector given by this. And now you can just utilize what we know with Rn, where we can actually start splitting things up. So we could split the sum of this, these components into two vectors, plus C2, B11, C2, B22, C3, B33. And then you could pull C1 out, A11, A22, A33, plus C2, B11, B22, B33. And then, of course, that is C1 T of A plus C2 T of B. So T is linear, all right? Which is good. All right, so then you want to show that the kernel is trivial. So we just let 0 equal T of A, right? Which means that this vector would equal 0, 0, 0, 0, right? So then A11 just equals and this is, I'm using A here again, but it's just arbitrary. There's nothing special about the A1. But all those basically have to equal 0. The kernel of this transformation is just the trivial 0 vector. So T is 1 to 1. And since T is linear, by that theorem I didn't prove, since T is linear, T is also onto. So T is an isomorph. I'm running out of room here. So T is an isomorphism. All right. And that's kind of the feel of all these things. You propose the map. A lot of times you start with here. You want to show the dimensions are the same, kind of argue that quick. That gives you the fact that they're isomorphic. Then you want to propose a map. Then, you go through the linear part, which is a lot of times if you propose an easy map, this should be fairly just tedious, but not super bad. And then I always think this is probably the easiest way to show that the kernel is trivial, which then, because it's linear, also gives you onto, and you have an isomorphism. So no need to work with just diagonal matrices in the 3x3 diagonal matrices world. You can just work with R3. This is the same thing as this. That's what this isomorphism is telling us. They are super useful and they're super common in tons of higher level math. Really all I'm going to ask you to do is stuff like this. But this is really the foundations of so much other stuff. It just opens the door to all sorts of cool problems in math.